So we're going to have our system again. Here's the system. Same deal, I have the temperature and pressure. And now what I'm going to do is I'll have an amount of heat del Q, and it will go to a Carnot engine and produce an amount of work del WQ, which simply means there's a temperature difference and this rejects heat at T0. So what we're doing is extracting thermal energy, and we have this form. We have other work forms as well. So if I look at this del Q, so del WQ is equal to del Q times T0 minus T. So we have that using the Carnot efficiency. And this is where we pay attention to del Q being negative because it's leaving the system. So del Q is negative leaving the system. And then what we can write is an equation for the net work. So I'm going to have del W net is equal to del W, and I'll explain that, minus P0 dV. And we'll talk about this because I have to displace the surroundings. So some of the network, when we introduced network in chapter 6, we had to displace the surroundings. So we're displacing the surroundings by P0 dV, so that isn't work that we have available. And then we're going to have T0 minus T over T times del Q. So what we did is we separated this work term is all work except the thermal work. All work forms. And so now we're going to manipulate the equation and get it into a simpler form. So we have del W net is equal to del W minus del Q. See, there's a minus del Q here, so I can take this out. Minus P0 dV plus T0 del Q over T. So when I look at this equation from chapter 8, del Q over T was the change of entropy, ds. So now we're able to bring in the entropy change here. We have these. And if I look at the first law, I have del Q is equal to dE plus del W. So dE minus dE rather is equal to del Q minus del W. Change of D. And then if I switch this, I have to pay attention to my notes and just not do things that I'm doing here. But anyway, with the point being that this term is the change of energy of the system. So the point being here that del W minus del Q is really dE, and so I can replace this by the change of energy, and we know what E is. And so then I have del W net is equal to minus dE minus P0 dV plus T0 ds. What this gives us then is this is the maximum work. So this del W net is equal to del W max. So this is the maximum net work that we could get by interacting with the system, with the surroundings. We're coming up with an expression for it, and it's the maximum work possible. This gives us an expression for the availability. So we're talking about the availability of a closed system, and this gives us an expression for that. So this del W max becomes our availability. And we'll clean this up in just a little bit, but notice that as dE goes down, as this decreases, so if dE were minus, I have a minus, a plus. So as the change of the energy goes down, the work availability goes up. So then, if I use our definition of E is equal to U plus KE plus PE, so now we can come up with an expression for the availability of a system at a given state. So we have the system at state 1, and we have the surroundings here at state 0. And so now we can get an expression for the availability at state 1. So we use this for the availability of a closed system. It's equal to m times. And now what we're doing is we're doing this per unit mass, and that's so if we need to look things up in the steam tables or pure property tables we can, or we can use the ideal gas law. So we have U minus U0 plus P0 times V minus P0 minus T0 times S1. There should be ones here. S1 minus S0 plus V squared over 2 plus GZ. And so this whole term is how we evaluate it. In example 9.1, goes through and shows you how to evaluate each term. So it has to do with the balloon up in the air, etc., and we can evaluate each term. If it's an ideal gas, you can use the ideal gas equation of state. If it's a pure substance, you look these things up in the table, all these. Notice here that we always have a difference, but over here we don't. And what's happening is this is the velocity relative to the surroundings, and V0 is 0. So this is relative to the surroundings, so there is no velocity of the surroundings. It's 0. So this is relative to the surroundings. Similarly, for the potential energy, it's relative to the surroundings. Now, often, so this gives us this example. It's how we want to find it. It's like, what is the work potential of a system at a given state? Very often, the system changes state. So we go from one state to another state. We want to see what changed, what the work potential was that changed. So let's write that down. Okay. So now, if we look at the difference in work potential as we go from one state to another state, equal to the change of internal energy plus the change of kinetic energy plus the change of potential energy and it keeps going. Plus P0 times V2 minus V1 minus T0 S2 minus S2. And so this whole expression gives us the change of availability as the system goes from one state to another. And we're looking at the change of work potential. So this is change of work potential. That's what this is providing us. So when that's the big concept here on how we do this. We have this work potential, and a system has it, and then perhaps it's been diminished. And so now we're going to take this and look at this availability with its work potential and look at this change and see what we have. So I've become fond of circle diagrams. So if this is our work potential at state 1, then we're going to have a transformation where we convert part of this into work, and then state 2 will have a reduced work potential. So that's, we're going to set up that scenario. Then at state 2, I'm now having this transformation. I'll have a certain amount of W reversible done, and this gives me A2. So of the initial work potential, sum is left as the availability, and the difference between the two is the difference between the availabilities. So W reversible is equal to A1 minus A2. Now, what happens actually is that in actual systems, not all the reversible work is used. So if I pull out this little sector, this pi piece, so this is W reversible. This is W actual. So we have the actual work that gets done, and then what's left over is stuff that's wasted. This is the irreversibility. So the irreversibility is work potential that is lost because of friction. Other irreversibilities, temperature differences between the system and the surroundings. So all those things come into play. And so we're introducing this idea of irreversibility now. So now what we're going to do is combine this with information from chapter 8. So we introduce the idea of entropy production. We talked about it in chapter 8, and I had mentioned that we didn't see why it was bad, let's say, but the entropy production is going to be related to the irreversibility, and so we can see the greater the entropy production, the higher the irreversibility, and it means that more work potential is frittered away and less is converted into actual work. So in chapter 8, we had that S2 minus S1 is equal to the sum of the Qi over Ti plus the entropy production. So we had the entropy production term. And now what we do is we take this equation and we put it in the one I just erased for the change of the availability. So we'll see what that looks like when I change it. We'll come up with a different expression for the change of the availability. Let me erase this. Okay. So we're going to combine with A2 minus A1, and we're going to get the following. A long equation. It's in the text, so you can see it in the text as well. E2 minus E1 plus P0 times V2 minus V1 minus T0 times the sum over the Qi over Ti minus T0 del SP. And we notice that from the first law, E2 minus E1 is equal to the sum of the Qi minus W. Just so we have that. So now, A2 minus A1 is equal to the sum of the over I of 1 minus T0 over Ti Qi. And I'll explain what that is. Minus W minus P0 times V2 minus V1 minus T0 del SP. So this is another way to look at the change of the availability. Some of the change was related to heat transfer, and the Qi refers to the surface temperature. So if I have a system, this surface temperature is Ti. And so when I have this Ti refers to the surface temperature of the heat. So the heat's going into the system or leaving the system, and you have to know what this temperature is to evaluate this term. This is called the heat availability transfer. And basically, it's that part of the change of availability associated with heat flow in or out of the system. This is work availability transfer. And obviously, this has to do with work going in or out of the system. This work is the work we figure out by first law analysis. So this is the work that you know how to figure out that we've been doing since chapter 3. And this is work against the surroundings. So the change in the availability has to do with the work potential. And so work is 100% work potential. And this term over here is the irreversibility. So the irreversibility is the loss of work potential. So this I, we talked about I, is equal to T0 del SP.